to ZTE University online course. And today's course is LTE access success rate optimization analysis. So today we will separate to mainly 4 parts to introduce you how can we do the optimization of access. So the first one is the access signal flow. You need to know the processing of the access. The second is the important steps of the access, is a random access. And the third one is the problem analysis. How can we do the optimization? And how can we increase the access rates? And the last one, I gave you a case to show you how can we do the analysis of the access problem. So let's start. Okay, so the first step is the analysis of the access signal flow. Before you know the optimization method, you need to do the access processing. So the UE, before the UE access to the InnoB, the UE need to send the preamble first to tell the InnoB that there's one UE want access to you, and the InnoB will get the response to the UE, say that if you give you temporary results and give me more information. And then the UE will send RC connection request, and the InnoB will respond to the RC connection setup. Those two is a high layer signaling, is the RC signaling. So in the random access, later we'll talk about, we have a message 3 and message 4. Actually, message 3 and message 4 sent in the same time with the step 3 and step 4 here. So when we do the optimization, we need to consider them. And the last one is RC connection setup complete. It means the UE establish the connection between the UE and InnoB. So after these steps, we have the connection. And then we start the UE and the EPC connection. UE will send the service request message in the RC connection setup complete. Actually, here we see is a service request message. We also can save attach request or DAU. So there will be the difference, depends the different requirements of the UE. Here, the UE send a service request because the UE there probably has some data to send to the EPC, or EPC has some data sent to UE. That's why it's a service request. But anyway, it's a lost signaling. It means the InnoB cannot read this signaling. InnoB can just transfer the signaling to the EPC. So then you can see in step 6, the InnoB transmits the service request directly to the EPC. And also, InnoB also added some information about itself, because after EPC will respond to the UE, the InnoB will receive the information and back to the UE. So in the step 7 is the processing between the UE and EPC, is the identity and authentication security. It's the security mode between the UE and EPC. And after this, we can see is the S1 AP. S1 AP is initial contact setup request. It means the S1 link established. It's the established between the InnoB and EPC. And then step line is not necessary sometimes. It's UE compatibility requiring. If in the step 8, if in this step there's no UE compatibility, and the InnoB will require the UE to send the UE compatibility. Actually, UE compatibility is the wireless compatibility, such as what kind of frequency band it supports, like this. So UE will send the information to the InnoB, and the InnoB send it to the EPC. And the EPC will determine whether this frequency band does the UE support and other information. Okay. And after 11 is the security mode comment. So this security mode is between the UE and the InnoB, okay? because in the authentication and security steps, we can see is the security mode between the UE and the EPC. But it also needs security between the UE and InnoB. So we have a security mode command of the 12th step. And after security mode, and then you can see it's RC collection reconfiguration. So this one means the UE establish connection between the UE and EPC, and the UE gets the DRB here. It's a dedicated RB, and UE will use dedicated RB to transmit data, and also the SRB2. The SRB2, before we see the SRB0 and the SRB1. SRB0 is the default SRB. It's a singular RB, and used to transmit the message 1, 2, and an RC connection request. Okay, and here and message SRB1. SRB1 we use to transmit the signal between the UE and the EBC, not InnoB. And here we have the SRB2. So SRB2 we use to transmit the signal between the UE and the EPC. Okay, so this is RB, the function, and then now I can transmit. Then after the RC connection reconfiguration complete, we can start to transmit the data between the UE and the EPC. And here is the first uplink data, and InnoB just transmit the data to the EPC and get the response. And this is data transmission. And after, if there's no more data to transmit between the UE and EPC, and the UE will start to release the UE. And first, the InnoB will tell EPC that please release detach the UE, and then the InnoB detach the UE, and the InnoB release the UE, and UE back to the idle mode. So we complete the one processing between the access and the detach release. So this is the full signaling flows. So now you know the signaling flows. And then what's the factor affecting access success rate? We separate two parts. The first one, the front-end test, is the test results from the terminal, and the back end. The back end is from the InnoB. So what's the difference? The difference is a random access. Do you remember at the beginning, we see that random access is message 1 to message 4. For all those 4 messages we cannot see from the back end because they are low layer signaling. So we can only check them from front end test. And then is RC collection setup and the ERAP setup, and all those two are same with the back end. So first 5 steps we call it RC collection setup processing, and after, before the RC reconfiguration complete signaling, we call it the ERAP setup processing. So they are all about the signaling. And then the radio access success rate is equal to the RC collection setup success rate multiply the ERAP setup success rate. So if we talk about the success rate of RC collection, we must need to consider the random access, because after random access is RC collection setup. Okay, and also after RC collection setup, we can see the UE switch from idle mode to the collected mode. Okay, and the RC collection success rate also easily be affected by the wireless environment. Definitely, for example, the interference, the coverage, also affect by the some parameters. So what kinds of parameters later we'll talk about. And the ERAP setup success rate. So the ERAP success rate, we have the 3 phrases. So the first one, the RC collection, and the second, the S1 collection, and the last one is ERAP. So actually, before the ERAP setup is the RC collection. After collection, RC collection, we have the UE to the InnoB, right? You remember? And after S1, we have a connection between the InnoB and MME, right? So you have the different collection, and the last one is from the UE to the EPC. So this is the three phrase. All those phrases, when we do the analysis of the access, we also separate them to these three process. And then, so what's the factor affect the ERAP? The first one, definitely wireless environment. Okay, and also the S1. S1 is the wire transmission. This is wireless transmission. They all affect the ERAP. Okay, and also when we evaluate our access rate, we use different performance, the KPI. So with KPI, we separate two parts. The first one is the accessible. So accessible, and the second one is the system availability. So this one, the system availability actually is a high level, and then accessible is the for the exactly some users or some sales. So first you can do this one, system available. For example, is the sale available? Sale is working or not? It's a system problem. And in an EROP setup block rate and a paging congestion rate. So this is system available. And second one is the accessible. This is exactly, it's higher accurate. Is the ERAP setup success rate and the RC setup success rate and ERAP setup success rate. So when normally we use those three, right? So normally this is the often we use to evaluate access. And the second part is random access and parameter analysis. So what's the parameter affects the random access? Because random access is so important in our access processing. And also, we need to plan the parameter in these steps. And this parameter also can be changed in our. So first, we need to know what's the series we use the random access. So the first series is the initial access. So when you open your phone, it's initial access. And the RC idle will change to RC connected. And series 2 is rebuilding after radio link RC equalization. And in series 3 and series 5, they are similar. So the main difference is the series 3 is the downlink asynchronization, and 5 is uplink asynchronization. So it means the series 3, the UE cannot receive the downlink signal, downlink message, and message 5, the UE can receive the downlink but cannot send out, but cannot reach the ENOB for the uplink. So this is the main difference. And the message and the series 4 is access to the new sales. Access to new sales, different handover, right? Handover, I need to random access. Okay. So this is the meaning scenarios for the random access. And in those five series, we can divide it to the different parts. We divide it two groups and depend on the contention or non-contention random access. So the random access, we separate them. The first one is the contention. It means we need to compete with other UE. Okay, so what is the situation in this 0, 1, 2, and 3 we just talked about? It means when the UE cannot receive the downlink message at once, I have to compete with other UE to do the random access. Okay, so in the random access, there's many 4 steps. Actually, we have talked about those in the signaling flow. The first one is the preamble. The UE sent a preamble to the ENOB, and the ENOB gave the temporary resource to send the message 3 and 4. Okay, and message 3. Actually, message 3 and 4 is the low layer signaling. And at the beginning, we talk about the single access signaling. Actually, is the step 3 and step 4. Those two signaling are sent in the same time with the message in the stage 3 is RC collection request and RC collection response. So they send at the same time, okay? But they can just only check in the terminal side. This is the, and then also the function of the message 3 and 4. In the message 3, and the UE will tell the InnoB that's who I am, the UE identity. Because in the message 1 and 2, the UE cannot know whether there's more than one UE use the same preamble at the same time access to me. Because the InnoB in the same time, in the one time, InnoB can just select one UE access to do the random access, okay, to access to it. So the message 3 and message 4 is the computation resolution. So the InnoB, if there's more than one UE want to access to the InnoB can just select one, okay. But the difference is here is a long contention based random access. So this one, we have one factor. So one factor is, we just talked about it. In the serial 4 and 5, the UE can receive the downlink advanced. So InnoB can give the UE that what kind of preamble you can use to do the access to me, and I will access to you directly. So in this situation, the UE already know the preamble it can use to access to the InnoB, and then the UE use this preamble to access to the InnoB, and InnoB just directly receive the accept the UE and then finish. So which one is quicker? Definitely, it's a non-contention based random access is quicker, but we have the limitation, right? We have the factors requirements. Okay, this is the two type of the random access. And what's the parameter affected the random access we need to consider? The first one is the seal attributes. The seal attributes we separate two parts. We separate two different seal attributes. The first one is the high speed, and the second one is long high speed. So this high speed actually is a frequency shift. It's a frequency shift. This one will determine that, okay, what's the average UE speed in my cells, and then this setting will also affect how can UE generate the preamble. So the first step, you need to determine your cells is high speed or not high speed. Okay, only those two steps, and then it's a preamble. So the preamble, in message 1 we use preamble, and in each cells we have 64 preambles, and all those 64 preambles comes from the row sequence. A row sequence. Actually, a row sequence is limited. A row sequence just have the A38 row sequence. But you see, there's so many cells, right? So how can those row sequences can generate such many preambles? So later we'll talk about how can we generate. But here we need to know those 64 preambles we divided to two parts. The first one is the dedicate. The second one is the long dedicate. You remember, we have the different mood of the random access, right? So in the computation, definitely we use this one, and in a non-computation, this one, okay? And non-dedicate, we also separate to two group. It depends on the message 3 size. If the message 3 size is big, and we use here is this one. It's 144 bits, but you can also say it's message 3 is 144 bits, or you can set it to 208 bits. So if message 3 is big, and you can use the group B. And if you use group B, it means your transmit power from UE will be higher, because you send more content, you need more power. But if message 3 is not such big, you can just use lower transmit power. Okay, this is good, right? And then this is preamble, And then we talk about how can the row sequence to generate such many primbles. We use first, you need to know what is primble. Okay, what's a primble? Where is a primble? Where is a primble? In the physics layer, you need to you know that the the function of P-rush we use to transmit the primble, right? And the P-rush actually the contents. First one is a CP, and second is a primble. Third one is a GP. Okay, and this is the sequence, the primble sequence. And also we have a different formats of the P-rush, depend on the different situation. The first one in format 0, 1, 2, 3, and you see the difference. The difference, first one, compared with this one and this one, the primble length is same, but you see the CP and the GP are different. A longer CP and GP means your coverage will be bigger. You see, your coverage was bigger. Your coverage, the cell radius is much bigger than the 1, right? 0, right? And then you compare this one, you see we have the 2 sequence. It means you have the deep coverage. You can receive the sequence better, okay? It's the deep, so when you use this one, deep coverage. When you use deep coverage, you use this one. And this one, besides you have more sequence, and you have longer CP and GP. So you have the longer cell radius, and also you have the better coverage. But the problem is this one, the message 3, the format 3, we have in the time domain is so long, is the resource consumption is big, right? So it depends. If the format 0 is enough, normally that you don't need to use format 3. Okay, this is the P-rush. And here to you, how can the row sequence to generate the primble? So the first one, and for each row sequence and also for each generated sequence, the length is A39. Okay, and then we choose the first one. We have low speed series and high speed series, and then when we determine this one, in the first we will determine the cell attributes. If your cell attributes is high speed, the high speed normally is higher than 120 kHz. That is the mobility of the UE. Okay, and if you high speed, and you can select your NCS from this table. Okay, from this table, it means NCS means, for example, we select 1. This is a configuration 1. Okay, configuration 1. Configuration 1 NCS is equal to 18. If you select 18, it means how many you can calculate how many row sequence you need to satisfy your cells. Because the first one A39 and divide 18. What does it mean? It means how many sequence you can generate by one row sequence, and you can see how many we can calculate. Okay, calculate. This one 46. Okay, 46. So each sequence you can generate 46 new sequence, and then how many primble you need for one cell? You need 64 sequence, right? 64 sequence. So you need how many row sequence? You need how many? 64 divided 64, right? 46. So you nearly 2. You need 2, right? So you need nearly two row sequence to generate the 64 sequence you need for the one cell. So the bigger NCS you choose, you see, the lower primble you can generate, and the more row sequence you need. So if we can select the smaller, because you can select the higher and higher so that we can save the sequence? No, okay, because a different situation. You need to consider different situation. And then normally we use this one, 46. 46 we use, okay, 46. It also related to your radians, stereo radians, okay. The stereo radians, you can see this one, stereo radians. If you select the big one, okay, you select such big one, this big one, and compare those two, you see the radians is different, right? Okay, so you need to consider radians. So this is the P-rush primer generation. And then, so next one is a P-rush transmission power. So this part we need to consider how can we transmit the preamble, because we need to determine, so what's the transmit power we use to transmit the preamble, the message 1, because normally if the InnoB cannot receive the message 1, it must be some problem. For example, it's coverage problem, or your transmit power is so weak. So transmit power here show you how can we get the transmit power of the preamble. So at the beginning, for example, we have the T1. This is the default. Is the initial power for the preamble. But once we send out the preamble, if the InnoB doesn't receive the preamble, we have the higher level transmit out power, and then higher, and then higher is the power wrapping of the power wrapping of the preamble. And here we just see that this is initial, and each step we have 2 dB upper, or 4 dB, or 6 dB upper, and then we have how many times? We have 8 times, maximum 8 times wrapping. So this is the power wrapping. Okay, the more times you transmit, the higher power you can do the preamble transmission. Okay, and here we also do the timing of the transmission. So all those timing is the random access timing. So when you send out the message 1, the UE will start the timing, the window size timing, to receive the message 2. So it starts when I send out the message 1, I start this timing. When I get the message 2, I stop this timing. Okay, and this timing we have a limitation. Is default is 10 milliseconds, or you can set to 2 milliseconds, 3 milliseconds, 4 milliseconds. So the UE send out the message 1 and wait 3 milliseconds, and I will start the TTI window. If the TTI window times out, and I will do the power wrapping. It means the first preamble, the InnoB doesn't receive. I do the power wrapping. Okay, and then is the message 3. Message 3 same. I also do the timing of the message 3 is the 48 SF. SF is the subframe. It's 1 millisecond. It's 48 milliseconds, right? 48 milliseconds. Okay, so it's the same meaning of the message 1. And here is the life. It's a dedicated preamble life. So what does it mean? It means when I send out the preamble, and this is the dedicate. Okay, dedicate. So it means the InnoB gave the UE advanced, but if the UE doesn't use this preamble to do the access after this time, and this preamble will be unuseful. Okay. So this is the parameter. And then the second one is the preamble, the problem analysis. The problem analysis will give you, we separate them. And you can see all those data will come from CXT and CXA. So those two actually we do the analysis of the log after the DD test. And then first we will determine whether attach field means and the UE failed to access to the EPC. And if there's problem happen, we will analyze what happened, what's the problem exactly in what steps has the problem. So the first one is the connection setup. And the second one, initial direct transmission, and then RC collection reconfiguration feature. So all those steps actually related to those three problems. So the first one, random access problem. Random access problem is simple, right? We have learned before. And authentication. Authentication, when we use authentication, is between a UE and EPC security, right? And the ERAP setup is between is a barrier between a UE and EPC. So the problem always happen in those three steps. Okay, we can separate them. So we separate them. Actually, random access actually is in the RC collection setup feature. Okay, so first is RC collection setup. So RC collection setup, how can we do the analysis? The first one, we just follow the signaling flow. Follow the signaling flow, the first one, the UE send the preamble, no or yes. If yes, we continue. Is UE received the preamble, ENOB received the preamble or not? And then the UE received, this is the message 1, right? Message 1. And this is message 2, right? Message 2. So UE received R response, message 2. And then is the UE send the RC request. RC request actually is the RC signaling, is high layer signaling. Also in the low layer signaling, we can see is a message 3, right? Message 3. So when we do the access, we can put them together. And this one is the received RC request. Okay, RC request, ENOB receive or received RC request or not, and then is ENOB send this is message 3, message 4, right? Actually, also we caught the RC setup complete. Okay, setup complete. So we can put one by one, step by step, and then finally we come to here. ENOB received the completion message. So this one, what it is, this is the message, is 5 steps in our first 5 steps. After this step, it means the UE and the ENOB established collection. Is RC collection setup finished? So RC collection setup, we consider those 5 steps, and then we analyze them one by one. The first one, does UE receive the message 2? Okay, so before we analyze whether UE received the UE message 2, we need to check whether ENOB received the message 1, right? Message 1, do you remember we send a preamble? We send a preamble to the ENOB. Does ENOB receive it? If not, what do we need to consider? And also this one we can check from the back end from ENOB side. We can check whether ENOB received. Okay, and we can check whether the received power of the uplink channel is higher than minus 99 dBm. It means is the uplink power is enough. Okay, if not enough, it means there is the weak coverage. Okay, if the weak coverage of the uplink, if it is exceeds 99, it means the coverage is good, but if the ENOB still cannot receive the message 1, it means there's the interference. Okay, also the GPS inner time slot interference. So those two. Okay, and then the P-rush preamble parameter adjustment. So how can we solve this problem? Increase the P-rush, expand receive power. So we can, if the power is not enough, we can increase the P-rush, expect receive power. And also P-rush power wrapping steps. What does it mean? Do you remember a parameter? The parameter means more power you transmit out, you can in after the ENOB side, I can get the preamble better, right? And increase the P-rush, the rush shot, the preamble rush shot. Okay, the price. So it means that you can increase your initial set out power, put out power, or you can increase your steps. You can send more times of the preamble. And then last, also you can increase your every time power wrapping. So every time you can increase more power. Okay, so all those steps actually in order to help ENOB to receive the message 1. Okay, and then it's a downlink. So this is uplink. Uplink we need to check, and downlink actually is a message to you back to the UE, right? If the UE cannot receive the message to you, we need to first consider the coverage. So this one is from DT test. From a DT test, we can check whether the coverage is good or not. Okay, and also is there any interference here? So is the PCI interference. So how can we solve this problem? Increase the initial value of the CCE aggregation. It means we increase the output power from the ENOB side to ensure that UE can receive the power better, receive the message 2 better. Okay, this is the message 2. And the message 3. Message 3 actually related to RC collections request, actually, right? If the message 3 cannot reach to the ENOB, it means RC collection request cannot reach the ENOB. Okay, and then the first one is to check the request message according to message ENOB sites. Okay, if the ENOB sites have not received, if ENOB cannot receive the message, there is some problem with the uplink. The same, right? If message 3, okay. So first, what do you need to check? Same. You need to check the coverage first, and then you check the interference. Okay, those two. And what need you to do? You just need to increase your power of the message 3. Ensure that ENOB can receive better. And then it's if the RC collection receive message 3, but the ENOB back the collection reject. So ENOB reject. So what's the reason for rejection? So normally there is a reason with the rejection. Okay, there's the 2 reasons. The first one is the congestion or unspecified. So congestion, if there's a congestion, you need to consider, okay? And consider what's the congestion. You need to check the network loading, or you need another frequency, another cell to increase your capability. So this is one message. Or is unspecified. Unspecified normally is not happen often, okay? Not happen often. So this is message 3, 4. And then, so here we summarize. We summarize the reason for the RC collection, and we also gave the solution. First, the reason, first one is the coverage, weak coverage, and the problem was of the uplink rush. So we means the preamble is weak, okay? And the third one is the unreasonable cell reselection. So unreasonable. So for example, your cell reselection is not in time, okay? And the UE does not initial access to the better cells. So this is all the reselection, okay? And the RS power and the power allocation power problem. So this is the ENOB site. The ENOB site cannot have the better downlink, so that you will lose the link. And then the congestion problem, because there's already so many UEs in my system, so that I gave you rejection. And device error. So device error, actually we can see the alarm from the EMS. So all those reasons will affect RC collection. And what's the solution? The first one is the RF optimization. So RF optimization normally we use to do the coverage, okay, coverage or cross error coverage. So it's the overlap, okay, overlap or weak coverage. And then so reselection parameter. So here is the late reselection or does not select the best cells, you can all change your parameters of your reselection. Okay, and also modify your random access and power allocation. So this one random access and power allocation parameters. Random access, for example, your power ramping, you increase your power ramping steps, you increase your initial output power, you increase your threshold, okay, or the power bias of a. So this is a PRASH, okay. We also do the PDCCH. How do you see CCE? CCE. We have the more aggregation of the CCE, okay, and modify the RS power. Modify RS power. We do the downlink. It's the downlink coverage. Downlink coverage is better, right? This one is the uplink. This one is the downlink. Okay. Now, when an authentication failure occurs, to make the analysis according to the reasons provided in the authentication failure message. So in this message, we can see the cause. The cause is meaning two types. The first one is MAC failures. So the main problem for the MAC failure is the UE illegal. And then the second one is authentication failure because the UE's key and it's different between the key from the HLR, from the collateral. And the second cause is the synchronization failures. So the main reason for this failure, the first one is the UE is illegal, and the second one is device error. Okay. And the last part is ERAP setup failure. So this one is so important for our access optimization. There's main 5 reasons for these failures. The first one is a weak coverage. The second one is the parameter, the configurations. And the third one is core effect. The core effect actually is related to the coverage, weak coverage. And the next one is a rejection from the UE and MME. The last one, device error. So we can have a look one by one. The first one is poor coverage. The poor coverage divided to uplink and downlink. And for the uplink coverage problem, it means the InnoB cannot do the demodulation and even cannot receive the UE message. In this problem, we need to check the RSS from the InnoB side to ensure that is there any uplink interference existing. And for the poor downlink coverage, it means UE cannot do the demodulation for the downlink. So in this part, we have the first one. We need to we do the RF optimization and just follow the coverage optimization. And RF optimization, we can change the titles to increase the coverage in this area. And second, or we can change the RS power. For example, we can change the current RS power to increase to have the better coverage. Or if there's the overload problem, we can decrease the labor RS power to have the better coverage in your local cells. And the last one, you can also have a new sites. So you just follow this process to fix the coverage problem. And then the second is UE doesn't reselect the best cells. It means you have the parameter problem. So normally, for example, the UE is changed from this cell. Is moving from the local cell to another cell. So at this moment, the UE will do the reselection. But if the reselection is too late, and then there will be the fissures, the ERAP fissures caused by the coverage, right? Because when you do the reselection, the coverage already so weak. So how to speed up your reselection? We have 2 methods. The first one, you can change your intra-frequency reselection threshold. Okay, so you can change the threshold to increase your selection. Okay, and also you can do your measurements better, measurement quicker to speed up the reselection. Okay, so this is the first one. Second one is a rejection from the UE or MME site. If the rejection is from the UE site, and you can see in the reason probably because of the UE problem, UE devices error, and you can just update the version or replace another UE to solve the problem. Okay, or if you receive the rejection from the enemy side, so you can just analyze singularly and the InnoB side and estimate the problem with the coverage quality and as one link feature. So if those two parts are normal, and now you can just move your problem to the core network team. Okay. The third reason is unreasonable parameter configurations, and just set the reasonable parameters. And in these serials, and then you have the access features. First, you check configuration. How to check configuration? Compare between the normal cells and the problem cells, whether there is some problem. There was some problem with the configuration. For example, they have the configuration difference. Whether this difference will affect your access rate. If yes, just change them. Okay, and then you will change your reselection parameters. For example, we just mentioned last, you change your reselection to have the speed up your reselection, okay? Or you change your intra-frequency measurement and the serial reselection at the same time, okay? To speed up your reselection. And then the fourth one is the color effect. The color effect is related to the coverage. So in this problem, you can change your RS power, okay, to have the better coverage in this area. Or you can make the antenna of the current cell transmit color in order to avoid the singularly period change process. So caused by the corner or the reduce the core features. So just to avoid the cell reselection in the core effect, so that you can reduce your ERAP setup features. And the last one is the device error. The device error normally because of the InnoB, okay? It's not the UE device, okay? UE device we have mentioned. This device error is the InnoB device. So if we found there's InnoB, if we found that the InnoB send the UE capability request, or we send the transmit the authentication between the UE and the MME, but there's no response from the UE, or the an ARC or NOC from the UE, it means there is a device error from the InnoB side. So you can check the alarm from the InnoB side, whether some equipment alarm and change your equipment, change your boards, or restart your equipment. If all those is no use, just move your problem to the R&D team, because equipment problem is not easy to solve. It's inside equipment. So now we move to the last part, is the one typical case we use to do the analysis of the access success rate. In this case, first we check that the RSP and the center of this cell is good. It means the coverage is good. But when the UE move to the overlapping area, only in the overlapping area, there will be the failure happens. So when we check them singularly from InnoB side, we found that there's no response from the UE. So when there's no response, we check the parameter, access parameter. We found that the row sequence and the NCS they use between the three cells are same. So what happened? So what's the function of row sequence? We use the row sequence to generate the 64 sequence in the one cell, right? Okay, so if they use the same row sequence and use the same NCS, it means those 64 prime sequence in each cell are same. So when the UE receive the message 4, it will receive the two same prime. So UE will face the problem. it doesn't know which cell I need to access to. So they will face the face the problem. So how to solve this problem? We just change the row sequence number. For the different cells, we change the different row sequence start. For example, for the cell 1 from 64 to 24 to 26, and the second one is 27 to 29. So if they use the different row sequence, even they use the same NCS, they can generate the different preamble sequence for each cell so that they can avoid this problem. Okay, so this is one typical case I want to introduce you. So this is the end for our course today. Thanks for your learning.